Hi everybody. Just a few more presentations before lunch. So we're almost there. I'll therefore ask the presenters to please try to keep up with the time. And we'll start this session on exploring the social, economic and environmental impacts of our SunCoChem project with a lecture by Enrique Lacasa, who will talk about that's weird. Environmental sustainability of the SunCoChem process, the life cycle assessment. Enrique himself is a researcher, as you can imagine, in sustainable chemistry here at the EURECAT. He obtained his industrial engineering degree at the University of Cantabria and his PhD a few years later at the University of Zaragoza. As you can imagine, of course, he's working as an engineer on environmental impact. He has over 8 years of experience as a sustainability researcher, and we're very glad to hear your talk today.
Thank you for the presentation, Bojan. I'm going to talk about life cycle assessment in the project of SunCoChem. Well, for this, follow these 4 points: brief objectives, case studies. We will see the results about these case studies, and finally conclusions. Okay, for the SunCoChem project, where the objective is to produce green chemicals, is a key point to evaluate the environmental profile of this technology, to identify the hotspots in this moment and could improve in the development of the technology. For this reason, the first objective is to carry out a life cycle assessment about the technology developed, to identify these hotspots and provide recommendations and measures to improve the technology in the level of the technology is maturating, and similar to eco-design criteria. Other objective was to perform a life cycle assessment for conventional production process. This is for comparison against life cycle assessment of SunCoChem. It's important to highlight that this comparison is not to determine that SunCoChem is better than conventional technologies, because SunCoChem is in early stage to development, but it's important to do this comparison because help us to have a base for the project and propose the measures and improve with the development of the technology. And also, other objectives is to evaluate the life cycle assessment or the results for SunCoChem with the energetic mix of today and the energetic mix planned for 2050, where hope that more renewable energies is as a source of this mix. And to highlight as a result, it's important that global warming with SunCoChem is reduced between 20 and 50%, and we evaluate the life cycle assessment with 12 indicators, and in this moment already SunCoChem improves 4 of these 12 indicators. Okay, as a case studies, first is lime-oxide, valeraldehyde, and we will see now, and glycolic acid. We have other 2 scenarios in the assessment. The first is the scenario of the project, SunCoChem, when we take CO2, we convert to syngas, and finally by hydroformulation produce, in this case, lime-oxide. The life cycle assessment take the evaluation of this process, collect inputs, energy, and outputs of the process. We compare this against conventional production process that take syngas from fossil fuels, and also we do other biggest scenario were contemplate a current energy mix and energetic mix for 2050 with more renewable energy. The objectives of both scenarios is compare the energy powered by hydroformulation. This is current and 2050. It's a very similar case for valeraldehyde, with both scenarios SunCoChem and conventional, both by hydroformulation, and the two sources of energetic mix. And, a small change for glycolic acid. We have the two scenarios for hydroformulation, similar to valeraldehyde and limoxal, but now in this case we take a three case, that is the production by electrochemical, where we capture the CO2 by SunCoChem technology and supply as an input by electrochemical process directly CO2 and not with syngas conversion. And other inputs and energy also is collected for this case. And well, with these three cases studies, I want to show the energetic mix that we have considered, a current energetic mix, and energetic mix planned for 2050 with a more percentage of renewable energy present. The objective of this was to, on the one hand, compare the benefits of SunCoChem in today, only SunCoChem technology, and the other is the potential for improvement of the technology if we could remove, in the majority of possible, the fossil fuels energy. Well, the first results for limoxal life cycle assessment we have measured by 12 indicators how product category rules of chemical products defined, and we compare the three bars are for conventional technologies blue, orange is for SunCoChem today, and green is for SunCoChem with renewable energy or 2050 mix. Here in the name of indicators, the cover defines which scenario is the best. Green is SunCoChem for 2050 and blue, as here, means that conventional technology in this moment is the best or the least impact. How the state of the development of SunCoChem today, we achieve already that 4 of these 12 indicators are the best, but must to highlight that SunCoChem has a lot of path of development to improve this. Then it's very important to identify these points to improve in the measure that technology is developed. And there are 4 blue covers that define that current conventional technology nowadays is the best. Then is very equilibrated, and the other indicators is very similar, with the difference of the last, that is the water consumption. We want to consider this because the values are very distortionated. This is because there are some process of SunCoChem that, who is in very early stage, is complicated to do a hypothesis for the processes will be comparable between them. Then we have some processes that water consumption is very distortionated, and we prefer so, but don't take in care. Well, and I want to put the focus on the global warming potential, because SunCoChem is a project with the objective to capture CO2, and maybe it's could be the most important indicator about the 12. Here we divide the CO2 or global warming impact in the stages or steps of the case study. Blue Blue bar is the CO2 capture, is negative because produce a compensation effect in the impact of the whole process. Orange is a conversion the CO2 to syngas, and in the conventional process measure the impact of syngas provided by fossil fuels. And gray, clear and first is the impact of hydroformulation, and I want to divide in two to see the energy impact that in energetic mix 2050 we can see how is reduced a lot. Nowadays the impact is very similar for SunCoChem and conventional, but it's important to highlight the potential for improvement that SunCoChem technology has if we consider a more sustainable or more renewable energy, how the improvement ratio 1% to 11% improve. This is the case for the valeraldehyde. In general results is very similar because we have 4 indicators where conventional technology is the best, and other 4 where SunCoChem technology is already the best. And the others is very similar, and how you can see we have the same problem with the water because it's a problem in the evaluation of SunCoChem technology. Okay. And it's a very similar result with a better ratio of improvement, with the description in detail of the global warming potential. In this case, we have a CO2 compensation, a syngas conversion that the process itself is highest than the fossil fuels, but we have to take into account the blue bar, that is the CO2 compensation, and the both for inputs and energy for hydroformulation. And in the same case, we can see how for energetic mix or with renewable energy improve a lot. The case of glycolic acid, I say that is a bit different because we compared against 4 or 5 technologies. In this case is blue conventional, both for hydroformulation process with current energy and renewable energy, and other was for hydroformulation with the same, for electrochemical with the same idea. Current energy, that is the biggest impact in the majority of the case, because now in the global warming assessment we will see that has a high energetic consumption, but also is the most improved for this reason, because when you substitute the energy source, current but renewable, there are a lot of potential. In this case, we have 4 indicators where electrochemical with renewable energy is the best, and only 2 where conventional technology is the best. In the others, there are variations between them and others. It's the same comparison than the previous 2 cases, but we have electrochemical and both with hydroformulation, with SunCoChem technology and with conventional technology. And also it's important to highlight the electrochemical potential for improve when we substitute the energy that take the biggest impact and consider renewable energy. The reduction pass to be the worst to be the best in this case. Also, it's important to highlight that electrochemical process is has the most captured CO2 or most compensation for its process is to consider. And finally, the conclusions of this study. It's important to highlight that the objective of the study is not demonstrate that SunCoChem is better or is the best, because as I said, it's necessary to develop a lot the technology, but it's a great opportunity to take this study to identify hotspots for apply in the process. But today, with the state of the technology in this moment, we can reduce global warming potential between 20 and 50%, depends the oxo product and the process. Also, in the 3 cases, SunCoChem is better in 4 over 12 indicators, and SunCoChem presents a greatest potential of improve if we change the energy, if we see the plan for 2050 for the energetic mix. And yeah, as I said, it's important to consider that SunCoChem is in a low TRL in this moment. And this is all. Thank you for your attention.
Thank you, Enrique. Moving on to our next speaker. So starting from LCA, moving more to the, let's say, social impacts of the project. Our next speaker is Antonia de Listelrooy from the International Hellenic University. She's been a professor in marketing for over 30 years in different Greek higher education institutes, and her main research interests are in the field of ethical consumerism and ecological consumer behavior. Antonia, looking forward to it.
So much different from all previous speakers. Together with my professor, my early professor, Irene Tilikidu, who sits at the next line of this room. We come from Greece and the Hellenic International University. We will talk about social impact assessment. My presentation will consist of 4 parts, the ones you see in the slide, but I will not repeat them because I will start with the research we have conducted to assess the social impact of SunCoChem project. We conducted 2 research studies. The first one was a qualitative research with 13 consumer packaged good industry experts about their perceptions of the SunCoChem technology and their willingness to adapt the SunCoChem OXO products. The second one, with regards to the second one, it was a quantitative research with more than 1,800 consumers, European consumers. It was designed and implemented in 4 countries with electronic interviews. The 4 countries were Germany, France, Spain, and Greece. I will move to the results of the first study, and with regards to the industry experts, the 9 out of the 13 interviewed expressed their willingness to adopt the new OXO products, but provided a list of prerequisites to do so. So they demand certified assurance for safety, functionality, efficacy, and so on, as well as cost reduction, availability of the OXO products, the availability of the supplier of the products, and of course, they need profitable consumer demand. As to the most valuable, crucial attributes of these green OXO products, they are mostly environmentally driven, as they demand assurance for the contribution of those products to the climate change combat, the reduction of fossil fuel consumption, of course, carbon neutral ingredients, product safety, efficacy, etc. It was notable that 7 out of 13 experts declared that they will leverage the adoption of these products in their promotional campaigns if they proceed with the final products. They all expressed skepticism about 2 points. The first one is the effectiveness of carbon capture and utilization as a long-term solution for mitigating climate change. And the second one, which maybe is connected to the first one, they expressed unawareness, they were not aware of the specifics of recycling CO2 technologies such as storage and convenience, duration of stock, quality of the recycled CO2 oxo products, durability of the final products. Moving to the next study, the quantitative survey with consumers, we used a combined theoretical framework, especially combined for this study. We utilized two very well-known theoretical models in ecological consumer behavior research. It was the theory of plant behavior and the values, beliefs, norms model. And this combination was enriched with three additional variables: the climate change risk perception, the media influence, and skepticism. Now, some of our results cannot fit in 10 minutes, so very summary. With regards to the four countries, most of consumers with higher education and earning incomes between 35 to 55,000 euros are more willing to buy those final products, that is detergents and cosmetics made with chemicals containing recycled CO2. In France, younger consumers, and in Greece, women are more likely to prefer those products. On the other hand, in Germany and Spain, students and unemployed are less willing to adopt those products. So, now, some implications for businesses and authorities. With regards to businesses interested to produce and deliver in the market the final products, they must understand that they can find their target group among people who think that it is easy and convenient to find and choose the new green cosmetics and detergents. These people are holding higher than other people biospheric values, climate change risk perceptions, awareness of consequences, which form ascription of responsibility and personal norms. These two, the last two, are impacted by close and important people pressure. There were fine differences among the four countries. So if a multinational company wants to produce and deliver products in the European Union, needs to know specifics about consumer behavior in its country. So French consumers will decide to purchase the green cosmetics and detergents, mainly if this action feels to be more easy and convenient. So marketing effort needs to focus on product design and distribution in a way that makes it more easy and more comparable with the regular offerings. Adequate labeling, extensive distribution, appropriate merchandising, price and quality competitive to the regular products, and of course, adequate communication may enhance the consumption of those products in France. In Germany, the German consumers are more probably buy those products if they feel the social pressure to do so. So communication efforts in Germany should incorporate important people, asking everyone to contribute to climate change mitigation by choosing the green detergents and cosmetics. In the poor south, Greeks and Spanish consumers need to feel either social pressure and easiness to do so. So they have two prerequisites instead of one. So marketing effort needs to produce products to be easy to find and competitive to the regular ones, as well as employ important persons too. Now, some concluding remarks, and that is the end of my presentation. We all must understand the academia, the policymakers and practitioners that most consumers are not capable, and they are not, of course, required to assess the environmental, the footprint, the ecological footprint of a product or service. So, especially in detergents and cosmetics, which are claimed to be sustainable, friendly, due to some chemicals which incorporate recycled CO2, it's very difficult to be comprehended by the consumers. Most people, most probably they have not even heard that CO2 can be recycled by modern technology. So any communication effort should be focused on informing and persuading audience, the large audience, with easy to understand and remembered messages, and combining techniques to increase people's biospheric, the sequence of people's biospheric values, which lead to risk perceptions, higher risk perceptions, higher awareness of consequences, and ascription of its possibility, which form personal norms in favor of pro-ecological behaviors, and in combination with behavioral control, perceptions of behavioral control, and the social pressure of impact of significant people may increase intentions, and this way may pave the way for the success of the new green cosmetics and detergents in the European market. So that was my presentation. Thank you for your attention.
Our next speaker, as part of this session, is Freddy Liendo, whom we happen to know from somewhere. But Freddy got his chemical engineering degree from the University of Central Venezuelan University, then got a double degree with the Polytechnico in Torino, where he also got his PhD, and has been working with quite a few years now on employing his engineering skill in order to save the world and tackle climate change. And he'll be talking to us today about the evaluation.
Yeah, well,
to
save the world, we also have to be sustainable in terms of economics. So that's what we see now. We will see now. So the techno-economic feasibility of the SunCoChem technology. I will try to be fast. So go directly to what is the opportunity of the SunCoChem technology now that looking at the taxes that are paying or will be paying in the next years. So this is opportunity to valorize the CO2 that could allow us to allows the technology to have a very interesting potential for be applied industrially. So with the technology that we have developed and we already have discussed about it, we are aiming at have a reduced capex and opex for to employ these novel modular solutions to convert CO2 and renewable energy into added value products. So we are at now at the tier 5 scale. So we are producing lime-oxal. I'm assuming under certain considerations based on the installed power of the plant, what is the productivity, the CO2 conversion, and of course considering some incentives that can have during the operation of the plant. So we have a syngas production cost of almost 4,000 euros per kilo of syngas, and lime-oxal 2,400. And if we do a scalability analysis, we can see that even if we're the prices of the investment will increase, will also be increasing the productivity, and let's say the direct cost will increase, but the indirect cost will be contained. So it will allow us to have a reduction of the final price of the products, as we can see here in the chart. We perform some sensibility analysis in which we consider how the variation of the electricity, for example, the durability or stability of the different components of the electrochemical device, as well as the CO2 allowance taxes that could be, and we thought that, for example, the electricity price, it has an effect, but seems that let's say the core of the process is fed by renewable energy or sunlight. The effect is not that high, because by increasing the scale, the consumption is optimized, the consumption of energy is optimized. So we also introduce not only electricity but thermal energy. So this is a very good point in comparison with the pilot plant that we have operating now. And by, of course, increasing the stability of the materials that we have, the prices are also reduced. But then when we introduce the analysis of the CO2 allowance taxes, it becomes very, very, very attractive. So we have a reduction of the price that is very important, as we can see, in particular for the syngas and also lime oxal. And so considering, considering now what could be the production production price of the lime oxal, that is the overall process that we are assessing. Considering that how the capex allowance tax can change in the time if we start producing, let's say today, the production price or cost of the lime oxal would be among 50 euros per kilo. So if we considering a contingency of the cost about 15%, and then also considering the markup of the product that we are producing on 30%, we could sell the product with on 75 euros per kilo. That will allow us to have a net present value that is very interesting compared to the investment that we have to do, and a payback period equal to 6 years. If we increase the price, because we still have window to increase it because of how the market could behave, so we could reduce even further the payback period and increase the return of investment of the technology. So as we can see, down to 3.5 years, and increase the return of investment to 200. So the main remarks that we have from this analysis is that the scalability sensitivity suggests that the scale up for considering, let's say, the Dow or IFF, let's say, productivities, the SunCoChem technology starts being competitive. The durability of electrodes and membranes is quite important on the economic feasibility of the technology. The energy costs affect less than 4% the production cost of our products, and the CO2 allowance taxes could play an important role in the final feasibility of our technology. And the market fluctuation could allow to have a feasibility technology to be introduced in the market for the production of the OXO products. So, thank you very much.
Thank you, Freddy, for being in time. And the only thing that is staying between lunch and us is this young man. So, our next speaker today is Eric Schuller from Avantium. Eric got his Bachelor's of Science in Biochemistry from the university in Bochum in Germany. Afterwards, he got a master's degree in chemistry and physics with a focus on CO2 plasma chemistry from the University of Amsterdam, where he also stayed for his PhD, where he used the CO2 for polymer production and ended up doing more or less the same at Avantium. So his passion is connecting fundamental science with process design to improve scientific relevance for industry. And Eric will be talking today about the opportunities and challenges of the SunCoChem projects, or rather the technology developed within the project in the chemical market. Thank you, Eric.
Yeah, thank you very much for the kind introduction. Yes, we heard a lot of numbers already today, so I will look a bit into the process. At the beginning of the project, we looked at the unique selling points that were promised. That was the idea of SunCoChem, and we had 3 main points here. That is the process intensification, and you have less process step. If you integrate those steps in one, you have a full integration of all processes. You have no high energy desorption steps if you capture CO2, like in amine processes, so you save energy there. And you don't need to compress or transport the syngas you make, which you do now if you want to do hydroformylation. Then the photoelectrochemistry was identified to have a potential to reduce the land use by combining things in one thing, and you don't need a PV plant, photovoltaics, and electrolysis, and you could potentially lower the footprint, which is important because suitable locations to actually do this kind of chemistry, you need to have a lot of sunlight. You have to have you have the ports. You have to have an infrastructure. If you look, there is not so many places, so scarcity is actually places where we can do that. And then the third one is that is a unique selling point that sort of goes a bit beyond the integration, and that's the transferability. Basically, hydroformylation, we focus on 3 main products now, but hydroformylation is a major industrial process which is used to make a lot of different oxochemicals. So if this works, we thought in the beginning we could expand this to other oxo products. So it's not just limoxal valeraldehyde, but also other oxo products. And again, if integrated, there's no transport of the syngas and the CO needed to make different oxo products. Where are we today? Well, I'll keep this really short. Basically, we did not manage to fully integrate that, but we developed 3 standalone processes. So we developed the CO2 capture, we developed the photocatalysis, and we developed the hydroformylation. Basically, if we look back at these unique selling points, what have we achieved? What can we offer to the market? We have a less intensified process. But we have then 3 steps we can apply in different markets, for example. So the CO2 capture we develop might be interesting for other markets. We still convert CO2 to CO using photoelectrochemistry, so that's still to be seen. We have to look, but land use, Enrique elaborated on that. We can identify that as something we have to look into further in the future development. Can we reduce the land we need? And the transferability is actually quite nice because we can make syngas. We've shown that. So we can use syngas actually also, and I will show this in a moment, use in other processes. So we can use, if we can use the SunCoChem technology to make syngas, we can even expand potentially the market there. So what were the proposed products of SunCoChem? We heard them a lot today. There's limoxal, there's valeraldehyde, and there was glycolic acid. So we have the 3 industrial partners, and a lot of what I'll show you is basically based on interviews I had with those partners, what they really look for now that they see what SunCoChem is about. Looking at the market, you have a limoxal. It's a bit difficult. It's a relatively small market. It's a bit mixed up because it's it falls under the fragrance and chemicals part, but of course, because we can also make other oxo products that also are used in this fragrance market, the market can be quite big. Valeraldehyde, also a relatively small part, and then but all of these markets have a growth potential. And then if you look at glycolic acid, that is out of the 3 is the biggest market at the moment, at least. And a bit more diverse. You have skincare and industrial applications, and there might also be future applications, which I will elaborate on in a moment. So there's the 3 SunCoChem products. Sorry. And yeah, so we see there is a potential. There's a growth potential of those. So also, if you need to expand the production capabilities, you could argue maybe in the future we can make also part of that with the SunCoChem technology. So we don't need to sort of compete with the old technology, shut that down. We have to make more of this stuff so we can make it from SunCoChem, for example. But let's look at something a bit further even. There's, if we look at the glycolic acid, we can also make biopolymers. So what are the expanded market opportunities? And glycolic acid you can actually use to make biopolymers. So not just oxo products, but also biopolymers. And you can see that seems to be even a bigger market. However, I've been a bit cheeky. I used a logarithmic scale here. So if you go back to the old scale, you can see that biopolymers, for example, have a huge market potential, a huge growth. We have to have a big petrochemical process. So if the SunCoChem technology can contribute to make syngas and to make these biopolymers, there's quite a big market potential in that sense, actually. Let's look at the other thing, the syngas. So that's basically, we can say we make biopolymers. Yes, there's a market, but what we produce at the moment is basically syngas. And for syngas, that's not just used potentially for biopolymers, but in a lot of industrial processes, we have the same story. Again, a logarithmic scale. It's basically similar to the biopolymers market. So you have 2 huge market potentials there. If you go beyond the oxochemicals and market yourself as a syngas producing technology. However, there's also a bit of a downside. With syngas, you have quite a lot of competition. You make CO and hydrogen. There's a lot of other technologies there. So that's a bit of the disadvantage that we reduce the integration of our technology. At the moment, if you look at syngas prices, syngas is quite cheap. There's natural gas conversion, there's gold gasification, biomass gasification. You have in the renewable sector, you have the electrolysis as a comparison. And if we look at SunCoChem, at the moment, the cost for syngas production is relatively high compared to those technologies. But of course, Freddie showed this already a little bit. We have, of course, the big CO2 problem on this planet. We have too much CO2. What is the potential to reduce the carbon intensity? And if you look at these competitive technologies, especially the really cheap ones, they have a pretty high carbon footprint. So natural gas, gold gasification, and biomass gasification, there is an intrinsically higher CO2 content. So if you then basically say we capture the CO2 instead of emitting it, basically, and you look at the CO2 prices until 2050 from different sources here, the CO2 price increases a lot. So if you then calculate what is your production price if you subtract the credits you get from using the CO2 up, then you can calculate roughly whether you get close to the production prices of syngas. However, you're not necessarily reducing your own production price, but what you're doing is you also increase the price of others, like the emitting syngas producers. they emit CO2, especially when they use, for example, fossil fuels they get out of the ground. Ideally, they would pay for taking the fossil fuels out of the ground. Then that technology should increase in price, and then you get to a point where you get competitive with these. Especially when you go to the 250 euros per ton, you're competing with natural gas conversion and gold gasification. I must point out, though, that this is at SunCoChem technology when you really intensify. So there is quite a lot of steps to do still until we also get to the productivity of where we can produce syngas at these prices compared to where the TRL 5 is, but there's 4 TRL steps at least where we can improve that. Yeah, then I come to the perspective of the commercial partners. IFF is a fragrance company. They're actively looking for replacements of currently fossil-based ingredients or reactants they're using to make their products. What they want is actually they're not so interested in developing technology. CO or syngas is a reactant for them. So what they want is, if they came to SunCoChem, they want to go to a company which sells a working technology that must be cost competitive, and having a greener technology is definitely a benefit. But if you look at the big molecules they're making, which are in formulations, then we have to realize that the CO that comes from syngas is only a small part of that formulation. So there is added marketing value. There is, of course, an overall greener product, but it's only a small contribution. That's why you can't exceed the price a lot necessarily. Dow Chemicals was mainly interested in the CO2 capture part. So if we have a CO2 capture technology, they might be interested, but similarly, at the moment they don't want to contribute in the development, but if you have a technology for CO2 capture, you could potentially sell it to them. We at Avantium, we have a strategic interest as a user of glycolic acid. We focus on making polylactic glycolic acid polymers. At the moment, we of course see also the SunCoChem technology a bit as a competition. We make it in a different pathway, the glycolic acid. From our perspective, using CO to make glycolic acid might not be the most competitive route in this case, because you still need formaldehyde, and you would need to also make the formaldehyde in a renewable way. But in that sense, it's good to see which competing technologies might be the best in the end. And yeah, we're happy to continue developing these and comparing these technologies so that we in the end find a good use case for each technology for getting a greener chemical industry in the end. Yeah, and then that's the whole technology, of course, but as we have 3 different steps, I want to highlight that there is, of course, also markets for the components that have been developed in SunCoChem. So we talked about the polysulfane membrane for CO2 capture. That's gas separation that is needed in lots of different other projects. So we have a patent now, so this might be really interesting for chemical manufacturing, environmental engineering, biogas upgrading, air purification, or industrial gas processing. So there is a market there, and that can be exploited further. We have the solar panels or solar modules, which are current matched or basically matched to the electrochemical process. Basically, it's a device which produces electricity locally, fitting to your needs. And of course, there is many applications which you can think of where you could use such modules. We now know how to make them. We can make them at larger numbers, so there are markets that can be exploited there. And example 3 would be the bipolar membranes. I picked that one also because bipolar membranes are a topic that needs a lot of improvement, and they're always, especially in larger scales, it's great to see that we have a new technology to basically produce these membranes and apply them, because there's huge potential increases in productivities in electrochemical reactors if you can get bipolar membranes to be stable and work well. So that is for sure a technology component that has been developed, and if this works and we develop this further, there is a big market potential for that too. With that, I want to thank you, and yeah, looking forward to questions.
Thank you very much. I would like please to ask all the participants in the last session to please come on stage for a short Q&A. We will of course start with local questions.
Yeah, thank you all very much. It was a pleasure to work with you on this project. I have questions about the LCA, 2 questions. The first one is an advantage of 20 to 50% was stated, but for instance in Limoxal, the CO that is in Limoxal is only 16% of the total mass of the final compound.
So you should get it for free.
So I would say the biggest part of the LCA is where the Limoxal comes from. Do you have any... So to me this looks like a difference. Do you have any explanation for that?
Yes, thank you for the question. The average of 2450 is an average of the whole project, but yes, as you said, in the case of Limoxal, has the lowest improvement in CO2. Then in the graph that I show, if you remember, the improvement is 1% in this moment, and I remember maybe 11 for the best cases. Then in this case, is not, or is the representative of the worst case, but the value 20 to 50 is an average of the whole project. Yeah.
And second question, if I may, you show that you get a credit for the CO2 that we consume, and the argument is that you capture CO2. But I think you should be very careful in claiming this CO2 credit, because if, for instance, when it's put in a fragrance, you take the CO2, put it in Limoxal, the Limoxal goes into a fragrance. Within relatively short time, the carbon becomes CO2 again. So when can you claim CO2 credit for storing carbon in a compound?
Yes, this is a good question, because had we hard work how to measure it, because it's very complicated in this moment. Yes, maybe for consider the effect of capture CO2, we take the best scenario, and it's necessary to check it in the development of the technology, because I think that the best way to validate it is measure in the real process, and maybe when it scale up. But yes, it's a bit complicated to have a detailed result for this. Yes.
Okay, thank you.
Okay, thank you very much for your inspiring presentations today. My question is for Freddy Liendo. You talk about a specific case of flue gas treatment. So all the syngas produced is used for oxo products formation, or maybe you could sell the syngas that it is not used in this case for the process.
Okay, yeah, thank you for the question. Well, in the case of a study that I presented, all the syngas that is produced is internally used or directly used in the oxo product production. So we are not considering the production, let's say, getting into the market of syngas, but it could also be analyzed. In a sense, in that case, we will need to increase, let's say, the scale of the productivity of syngas, covering also the oxo production, let's say, case. And we could also have, let's say, this scenario, but it doesn't have been analyzed yet. Anyhow, considering the CO2 taxes that are, let's say, avoided by reutilizing the CO2 that is captured, the syngas price that came out, it's competitive, and or even for a bigger scale, the competitive is higher, so it could be assessed. So it could be a good scenario, but for a bigger scale, I think. Thank you.
Thank you. Thank you all for your very clear presentations. I'd like to make a comment and then ask you to comment on that. I have seen and realized actually today that when you analyze the life cycle assessment, the sustainability of our process, actually there is a huge contribution to the CO2 equivalent emissions of the hydroformylation process itself. Much more, I mean, this is the main contributor, if I have seen well, in the total impact of the technology, SunCoChem process, final technology that we developed. So I was asking myself if we are able, maybe in the future, in SunCoChem 2 projects, to actually make what we originally liked to do, that was to integrate also the hydroformylation inside the same photoelectrochemical reactor. So how that could impact either the CO2 equivalent emissions, the sustainability of the process, and also how can we enhance our economic impact. So from your point of view, the sustainability and the economical feasibility of our process, how could be improved if we are able in the future to integrate the technology in tandem?
Okay, thank you for the question. Well, in first place, it is because syngas is maybe small in the contribution of the whole process, but in the case of hydroformylation, the most impact is about catalyst materials, because there are some products similar or in part of rhodium, for example, that contributes a lot. In the case of hydroformylation, I think that this is the most contributor. And in the case of electrochemical is energy, but in hydroformylation is not the case of energy. Yeah. Maybe I answered your question.
I mean, in principle, to comment on that, if we are able to do in an electrochemical reactor the same process, we maybe have to use also rhodium-based catalyst, but in a much lower amount that you need in a homogeneous reaction. So in that sense, we can have an improvement.
Yeah. We could analyze the contribution of more in detail inside of the hydroformylation, because here it was a general value. But yes, I think that the most of the impact comes from catalyst materials.
Last question from the audience before we move to the online questions.
Yes, I'll try to be very quick. So thank you all for providing this overview. I have a question for Antonia. I was wondering if the people living in a single country know that other countries are being active towards the selection of the products, let me say, more green, if this could change their perception, because maybe they can see that it is not a matter of their single country, but is a general effort that maybe can, I don't know, push people to say, okay, we are not alone, so other people are trying to focus on this, and maybe this, I don't know, just a curiosity. Thank you.
Okay, thank you for your question. I really do not answer questions that I have not asked them to the interview. So we didn't check for that. We checked only for the what perceptions the other close to people, other people think. So my friends, my family, my relatives, my colleagues. Social pressure is one of the variables that can enhance consumption of green products, especially in Germany, but in Greece and Spain too, and other countries too. So I don't know about the other countries, but close people to a consumer can persuade, can motivate a consumer to act in favor of the environment too.
Thank you.
So, moving to the questions online, I'm afraid we will not be able to answer all of them, but let's start with Eric. So we have a question: how does the missing integration of the hydroformulation have an effect on SunCoChem as such?
I think what we can say is that it mainly changes a bit the target audience of the technology. Because if there is existing so from the perspective of companies which do hydroformulation, they have a process that is highly developed. It's been running for decades basically, so it's been highly optimized. So they of course know their technology. So if you talk to them, what they want is they want to have a different feedstock that is made from CO2 or from renewable carbon. But it has to have the same spec. It has to be cost effective or cost competitive. And then you have to see, depending on the product, let's say, for example, Limoxal is a bio-based starting material. If you then can say, well, we don't have a 100% renewable product, let's say if you, for example, then the missing piece is only the CO from SunCoChem, that is then renewable, you might maybe have a different message, and it might be more valuable than to add this missing piece. But overall, not doing the hydroformulation basically makes you a syngas producer that has opportunities, a much larger market, and you might also find niche applications in this case. But of course, you also have more competition. That is mainly what it does. Yeah.
Moving on to Antonia, do you think this marketing effort of multinational cosmetics and detergent companies should design a distinct and specific marketing plan for each European or non-European country?
Yes, multinational companies already know that they design a product for the whole world, but they have to market it domestically, so they have to build maybe a different version of the same product for a different country. So yes, they have to build a separate marketing plan for each country or for each audience. If they have the information provided about the consumer behavior. So if they have that information delivered from our consumer survey, yes, they have to do it. If they want to increase sales and ultimately their profits. So.
Okay, and last very fast question to Freddy. Have the results from the LCA and techno-economic analysis been published, and do we plan to publish them?
No, they are internal results. Yeah.
Okay, thank you very much. So with that, I would like to close the session. We'll go for lunch. We'll try to be back by 2:30. Let's see what happens. A final sort of request to our online guests: please, when you ask a question, please note to whom the question is being directed to. This will make the life of the chairperson much easier.